some theoretical stuff in reinforcement learning, like TQ network and policy gradient and the TPO. But now we are going to study some practical stuff, how such kind of algorithms can be used in real world. There can be many tasks we can utilize reinforcement learning algorithms, and I guess these days the most representative example would be robots. And behavior cloning, imitation learning. Behavior cloning is some subset of imitation learning. Imitation learning is one of the most widely used approaches for training robots. So we are now studying imitation learning, and behavior cloning is the first part of imitation learning. So from its name, we can know that it tries to mimic some behavior, right? Clone means copying, so copying some behavior. There are many some words that people say, like learning from human demonstration, behavior cloning, all this kind of stuff refer to some similar things. So let's first recap exploration-based RL. We've so far studied many algorithms, right? TQ network, policy gradient, PPO. Of course, there are many variants in TQ, PG, and PPO. Rely on agents' ability to stumble upon the reward via random exploration. So we haven't actually considered how can we design reward. How can we design reward? What is the good reward function? And it takes actually without proper reward design, it could be, the algorithm actually cannot find some good convergent point. It takes millions of environment interactions to find needle in the haystack, and exploration noise like epsilon greedy, Gaussian is isotropic and undirected. And to make this kind of algorithms actually work, we need human effort. It requires painstaking reward shaping to guide the agent. I guess maybe you guys start the final project and you realize how much this is difficult in your final project. So in your final project, I remember most of the things are already, why it doesn't work? Okay. So most of the PPO algorithms are already implemented, and maybe I guess there are many stuff you need to implement. Not only reward, but the majority of your time will be in designing reward function. What is the good reward function to accomplish your task? And how much there can be multiple combinations of multiple reward functions, and you need to make a combination of multiple reward functions, and how much you will give weight to each reward function. That is also depends on your design choice. Depends on your experimental result, depends on your design choices. And this is actually not very easy. It requires lots of engineering and lots of heuristics. You need to design proper reward function, and that requires human effort to make this kind of algorithms actually work in real world. So without, the reward function depends on your reward function design. It could be very sparse or dense, but without proper design, the reward function could be very sparse. Sparse means most of the exploration you tried result in failure cases. Your agent cannot get positive reward. Most of the exploration gives you a negative reward, then your agent cannot learn anything, right? That is sparse. Majority of the reward just a meaningless reward. So in tests like high-dimensional humanoid walking or bimanual manipulation, bimanual means two hands, bimanual manipulation, the probability of reaching the goal by chance is near zero, right? There can be many, high-dimensional means there can be many possible actions, right? And in your trajectory, all these kind of sequential trajectory, without proper reward design, the probability of reaching the goal by chance is near zero. The agent gets zero reward for 99%, of its life, without the gradient to follow, learning never begins. That is obvious, right? Of course, we learn many techniques. Of course, we learn, for example, in DQN, we learn PER to address this kind of meaningless reward for most of cases, right? We save some training data based on their time difference errors to address such difficulties, but still, for high-dimensional tasks, actually designing reward function is very challenging and important. And the critical question is, what if we already know a good way to perform the task? Why force the agent to rediscover it from scratch? That is today's question. And imitation learning provides a warm start by bootstrapping from expert knowledge. That is the motivation of imitation learning. Without enforcing your agent starting from scratch, let's say we have some good reference. I'm not sure, that can be from human demonstration for any cases. If let's say we have some good reference, then why now we utilize them? That is the motivation of imitation learning. Okay, so and actually I already introduced this kind of human demonstration at the early of this class, a teleoperation. Teleoperation, remotely controlling robots. We wear some exosuits and then we control robots remotely. By doing this, we can somehow get human demonstration, right? That such kind of human demonstration, human trajectory could be a good reference to train robots to mimic human behavior, right? Instead of training from scratch, there can be many random behaviors, right? Instead of doing such kind of many random variables, we can tell robots, follow human behavior. And to this end, we need to digitize human behavior, and then we need to store human behavior. That is the teleoperation, one of the way to digitalize and store human behaviors. And teleoperation, still these days, the most widely used way to obtain robot data. But also it is, it has drawbacks. As I introduced, this is not scalable to unconstrained in the wild environment. For example, we cannot use such kind of complicated devices in outdoor. We need to maintain this kind of device in outdoor. That is not very easy. Also requires expert level control technique, as this video shows, the right video shows. Playing instrument, piano or electric guitar with this kind of exosuit is not easy. Nevertheless, it provides clean robot data, clean robot trajectory. That is good. And then we can tell robots to follow, mimic human behavior, which is obtained from teleoperation. Of course, this kind of human getting data, learning from human demonstration stuff has been started a long time ago. ICML 2004, NeurIsh 2007. Let's say there are many video games, right? There are many racing video games, and then we can control our car in the video game environment. And then we can record such kind of data, and then we can use such kind of recorded data to train a self-driving car, right? Because getting data from real environment is not very easy, so that we can use some simulated environment to get the self-driving car, and then use such kind of data to train self-driving car agent. Parking lot navigation, all this stuff. Well, let's define this informally. Imitation learning, in short IL, is the process of learning a policy, pi theta, that performs a task by observing demonstration from expert policy pi star. Expert policy could be another policy function, or human demonstration, or some video game, simulated video game, anything can be expert policy. The objective match the expert behavior without necessarily knowing or observing the explicit reward function. That is the objective of imitation learning. Not very strict, roughly saying, but of course we can introduce reward function. We will see this later. Without reward function, there can be some problems. So we can still introduce reward function, but the main objective is match expert behavior without necessarily knowing or observing the explicit reward function. And here, the data set, the expert data set, It consists of just a pair of state and action. From current state, what is the desired action, right? State, that is just the input output of policy function, right? Policy function. Policy function takes state and output action, right? So that, and then we can, that becomes very typical machine learning problem, supervised learning, right? If we have a pairs of input and output, we can just train our policy function with supervised learning. To this end, of course, we need data. Lots of pairs of input and output, which are state and actions, respectively. Data can be sourced from human teleoperation, motion capture, legacy algorithmic experts. Anything can be used. Of course, if we get better data, the quality of policy function could be better. But any data can be used in theory to train for the imitation learning. And let's compare our previous reinforcement learning algorithms to imitation learning. The primary goal is maximize cumulative reward, right? So far we've studied lots of reinforcement learning algorithms, DQN, PG, APO, all this kind of stuff. Always try to maximize cumulative reward, right? But here, imitation learning, some extreme part of imitation learning, it does not introduce reward at all. It tries just to mimic expert behavior pi star. And required input is reward function, but we need just expert demonstration, which is the pairs of state and action. And human burden designing consistent reward here. Designing consistent reward, but here collecting and filtering teleoperation data is what we need to do. And convergence, slower, start with zero knowledge, right? So as I introduced, RL, the nature of RL is exploration. It tries to explore many directions in parallel, thousands of environments, and then tries to find positive reward. And then our PPO, for example, tries to encourage our agent to repeat it again. That is the nature of reinforcement learning. But on the other hand, imitation learning, much faster. It's almost like a supervised learning. So let's say we have an expert demonstration D, and then we can just perform supervised learning, the typical machine learning algorithm. Generalization learns optimal behavior via trial, but limited to expert scene states. That also makes IL, imitation learning, suffer from generalization. We'll see this later. And as I said, there are many algorithms actually. There are several algorithms in imitation learning. Behavior cloning, as I said, is the most one of the basic algorithm in imitation learning. So behavior cloning in BC, in short BC, maps state directly to action by offline supervised learning using expert demonstration. And it's the simplest baseline, but suffers heavily from compounding execution error. We will see this later. This is the most simplest one. We can come up with just supervised learning. Let's say we have an input and output, and then we just supervise the desired output from our data set. Interactive imitation learning. Dagger is one of the algorithms that belongs to this category. An interactive extension of BC, where the agent collects its own trajectory and receives real-time action label from an online expert. This iterative loop effectively mitigates covariant shift problem. We will see this also later. So it seems like interactive imitation learning, or Dagger algorithm, is the kind of combination of behavior cloning and reinforcement learning, right? It still tries to receive real-time action labels from online expert. At the same time, it tries to collect own trajectory as well. So it does some kind of exploration, and it tries to get some benefit from supervised learning as well. We will learn Dagger next time, maybe. Anyway, there's a second category, interactive imitation learning, and inverse RL, in short IRL, recovers underlying implicit reward function that explains expert demonstrated behavior. It seems like very interesting, right? From human demonstration or any demonstrated behavior, it tries to discover implicit reward function that explains expert demonstrated behavior. And once the reward is inferred, the policy is optimized using standard reinforcement learning, right? That is also one way. Because, as I said, designing proper reward function is very important and not easy, so that what if we can just discover proper set of reward functions from raw data, and then we can use such kind of reward functions to train our policy function. That is the motivation of IRL, inverse RL. And final one is generative adversarial imitation learning, in short GAIL. Leverage the generative adversarial framework. This is GAN, where policy access generator and the screener minimize divergence between agent and expert state action distribution. Unfortunately, this one, IRL and GAIL, are not widely used these days. Actually, funny thing is that these days, just BC is the widely used. Although this is very simple, what we have these days is large-scale data, right? We are living in large-scale data era, and there are many problems in BC. For example, the representative problem is compounding execution error. But what if we have tons of millions of billions of data? Then just it somehow works. So that these days VLAs mostly just use BC, behavior cloning. I'm not sure that is optimal. I think there's still a research topic. What is the good approach to train some robots and VLAs? But these days, simply just using behavior cloning is the primary strategy to train VLAs. As I said, behavior cloning, BC, is simply a subset in imitation learning. There are many categories in imitation learning, but behavior cloning is the simply a subset. Most basic form of imitation learning ignores sequential nature of tasks and treats control as supervised learning. The hypothesis is that if we learn function F, policy function, state to action that expert uses, we can perform the task by simply running F on our own observation. And this is just a mathematical definition of loss function for behavior cloning. For continuous control, we can use mean square error, right? L2, L1, anything you can use, but it's just an example of continuous control. This is the output of our policy function, right? Which is action, and A expert is from our data set. We have pre-recorded data, which is a pairs of state and action pairs, and then the typical supervised learning, right? Let's say our policy function outputs some action, and then we have desired action from our pre-recorded data. We'd like to minimize distance between them. That is for continuous control. For discrete actions, we can use cross entropy. Likewise, we do in image classification to maximize likelihood of expert choice, right? Ultimately, performed by standard gradient descent using Adam or SG optimizer, just like image classification. So nothing to think very seriously, right? Just use lots of data and then just do optimize neural network. Likewise, we do in image classification or in object detection. And here, I'd like to introduce the rationale for learning from human demonstration is that the core philosophy for this, introducing this kind of imitation learning is that bootstrapping from biological priors. The human demonstrations represent highly optimized, structurally organized trajectory crafted by an intelligent biological controller, which is human, right? We already familiar with this kind of environment. We know how to manipulate this kind of object, right? So that it is actually very natural to come up with this kind of imitation learning. We'd like to, let's say we have a kid, we have a baby, and of course we teach our baby to manipulate this object. This is rigid, or there's a button. You need to control this remote controller by pushing this button. We always teach our kids, our baby, to manipulate object by teaching how humans actually interact with this kind of object or scenes, right? So that is the motivation of imitation learning. We have lots of human demonstration examples and then just utilize such kind of examples to teach robots instead of training from scratch without any knowledge, right? So it's actually very natural to introduce this kind of learning from human demonstration, in my opinion. So human demonstration represent, and instead of forcing agent to discover safe and functional behaviors by chaotic blind exploration, we utilize human data as a foundation prior to constrain the search space. It's very natural and straightforward, but actually technically not very easy. There are many challenges, but one of the representative one is embodiment gap. Humanoid is okay because humanoid typically have almost the same anatomical structure with human. Two arms, two legs, body, one hand is okay. But what if we need to teach some spider-shaped robots? Spider shape. There are like 8 legs, and it tries to move around this environment, and it tries to, for example, carry some object or move this desk. How can we teach it? We cannot. I mean, expert level actors can move like spiders, but most of us, including me, cannot move like spiders, right? How can we teach? So that is very interesting research topic. I think using human demonstration, we need to do that, but it's very technically challenging to transfer human behavior to spider shape or arbitrary object shape, right? So it needs to be addressed. It is still work in progress. Anyway, but this is rationale for learning from human demonstration. It is very natural to introduce human demonstration in robot learning because we have lots of data. We have lots of experience. We evolved from, thousands of years to interact with this world. And actually, all these objects are designed to be interactive with us, right? This remote controller is very good for our hand. It's designed for humans. All these objects actually are designed for humans, right? This desk, it has a good height, right, for me. For most of us, has a good height. We can put our iPad on this desk and then write something. Let's say this desk is like much lower height than this one. It is not very comfortable for us to write something on very lower desk, right? So all this desk, chair, elevator, all this kind of stuff are designed for humans, right? So, and we know how to interact with this kind of object, so utilizing such kind of knowledge is very natural. And it can be used for many imitation learning or reinforcement learning algorithms. For example, utility in behavior cloning, sample efficiency, as I said, directly mapping human observation state to corresponding expert actions, allows the policy to bypass sample heavy and trial error phase, provides warm start policy, transforming a complex exploration problem into highly sample efficient function, approximation task, and reward-driven reinforcement learning. We've studied this one, overcoming sparsity. In high-dimensional robotics, for the bimanual manipulation, the probability of finding a sparse environment reward by chance is near zero, as I introduced. Human demonstration serves as a macro-level guide, whether used for initializing the policy network or shaping dense reference reward. They prevent agents from getting stuck in zero-gradient reward landscape. So the unified value is that regardless of downstream algorithms, whether copying action directly via behavior cloning or aligning trajectory geometries via reinforcement learning, human demonstration provides the essential semantic and physical anchor needed to make complex robot learning mathematically and practically tractable. So that is the rationale and value for learning from human demonstration. But as I said, it is not easy. There are many challenges. I introduced embodiment gap, that is obvious one. But another one is the missing action problem. So let's start with this one. Philosophical shift, learning from passive data. Scaling robot learning requires shift from high-cost robot teleoperation to utilizing abundant passive web-scale human videos. Let's say we have an exosuit. And then like this video. We have exosuit and remotely control robot. And then in this way, we can directly get robot data, robot action data. Action means the target of PD controller. In your final project, there is a PD controller which tries to map the targeting joint rotation to a force and torque of each robot joint. That is a PD controller. And by using this kind of teleoperation devices, exosuit teleoperation devices, we can get action data. But how about the human video? Or there can be many demonstrations that are not recorded with teleoperation devices. Then the problem is that we do not have actions. It is not restricted to human video. For example, let's say we have motion capture, mocap. In you know the motion capture? We have, let's say in making video games or movies, we have like a studio and then actors wear some suit and then markers are attached on their body and then the cameras, IR cameras track actors' motion. That is the marker-based motion capture. Marker-based motion capture or markerless human capture with human videos, all this stuff provide a position or rotation of human joint, right? It provides position, let's say position of human joint. Likewise, our final project. Our final project provides you the position of hand joint, right? And object orientation and object position. They are from mocap. They are from multi-view markerless motion capture. We can, using computer vision techniques and multi-view geometry theory, we can get motion capture data. Marker-based, markerless, anything, we can get some with enough number of cameras, then we can get some reliable data. That is called kinematic data. So let's say kinematic data. Kinematic data. These are from mocap. Kinematic data, as our TAs introduced you, kinematic data, it suffers from physical implausibility. There can be penetration between object and hand. There can be hovering problem. The object and hand are not contacting. So visually good, but physically it does not make sense. That is a kinematic data. So we can get kinematic data using multiple cameras, computer vision, and anything. We can get kinematic data, but for example, for making movie, making game, or video generation, physics, of course it matters, but not very important like robots. I mean, for example, making movies or games or video, generating video, as long as visually pleasing, it is okay. Does not matter it is physically implausible or not. Out of the field of view, we only take care about the render video, right? Out of field of view. It does not matter what happened out of field of view, right? So for like a rendering or video generation, physics is important, but not very important as robots. Because as long as visually pleasing, it is okay. So most of this movie, game, or video, kinematic data is enough, most of cases. But robots, it needs to interact in real physical world, and kinematic data is not enough. So although we provide mocap data to you in final project, as our TA showed you, once we lift the kinematic data to the simulator, you saw the video, right? The object just fall down, but there is no enough contact between object and hand. That is all videos included in the tutorial that our TA showed you. So that means missing action problem. Although we can get kinematic data from motion capture or computer vision, whatever, they are physically inconsistent. For rendering-based applications, game, movie, or video, anything, it is okay as long as visually pleasing. But for robots, it is not okay. Visually pleasing is not enough. We need to make our robots physically consistent, plausible, that it can interact with our real world in physics law, right? That is the missing action problem. Although we can get kinematic data from mocap, we do not have action. Our policy function, for the behavior cloning, we need state and action, right? But for mocap or human video, we have state. We have state. State means like human joint positions, but we do not have action. So that from mocap or human videos, we cannot do behavior cloning. So we need D equals to SA, right? I equals to 1 to N. We have S, but we do not have A. If we use teleportation data, then we have all this S and A. But for motion capture or markerless motion capture from human video, we do not have action. we do not have action. That is missing action problem. We do not have action. So that we cannot try behavior cloning. That is the problem. Although introducing learning from human demonstration is good, only with special devices like a teleoperation, we can get this kind of data. But for many cases, motion capture, we cannot get action data. So that we cannot introduce behavior cloning in many cases, unfortunately. To address this, there can be some ways to address this missing action problem. Inverse dynamics model. Train a separate model or small robot dataset for predict action T from only state. The state, as I said, we can get state from kinematic data using motion capture. This IDM is then used to label millions of human video frames with pseudo action for offline behavior cloning, right? We can train a small policy function to make a pseudo action labels for all state data, and then use such kind of pseudo action labels for offline behavior cloning. That is the one approach we can try to address missing action problem. And second one is our final project. Video-driven reward plus reinforcement learning. Treat human video as a reference trajectory. We do not provide you human video, but we process all the human video and then we just provide you mocap data. We provide you kinematic data. And then we can use this kind of kinematic data as a reference trajectory and use visual alignment metrics, distance between your agent and our kinematic data as metrics to define dense reward function, allowing the robot to discover valid action through online reinforcement learning, like BP or soft-actor critic. This is our final project. So your reward should include, for example, distance between kinematic data and your agent joint position, such kind of thing. Similarity between our provided data and your agent state. That can be one reward that you can design. And this is our final project, right? And this third one is foundation VLA alignment. Leverage the heavy semantic priors of large pre-trained visual language models. Human video train the model what to do conceptually, while a small pool of robot data aligns the tokenized output into precise physical execution. We will learn VLAs later, but as I said, getting action data is not very easy because we need teleoperation data, so that instead of training robots VLAs on huge scale teleoperation data, we can train VLAs. Likewise, we train LLMs, and then we can fine-tune our pre-trained VLAs with small amount of teleoperation data. That is the third approach. We will see this later. Anyway, the IDM is the first approach that we can try to get action labels from states. Where states are from human video or motion capture. And the second one is video-driven reward plus RL. This is our final project. Treat human video or kinematic trajectory as a reference trajectory, and then use visual alignment metrics, use distance metrics between our agent status and then human trajectory to minimize distance between them. So that without action label, so this kind of second approach, we do not have action label. The first one, we have action label. We can get action label from pseudo ground truth, right? But then for second approach, we do not have action label, but we can indirectly tell our robots to follow our humans by designing reward function to mimic human behavior, right? That is the second approach, our final project. And one, actually, I introduced the covariance shift, right, in the early slide. One of the problem in behavior cloning is the IID violation. I introduced that behavior cloning is almost like a supervised learning, right? But the supervised learning, typical supervised learning and machine learning, relies on IID assumption. Data points are independent and identically distributed. That is the assumption of supervised learning, right? All these data points are independent and identically distributed. That is the assumption of supervised learning. So in standard supervised learning, we have, let's say, image classification. If you misclassify a cat at index n, let's say we have a video. video, and frame n. Frame n plus m. If you misclassify a cat at index n, and let's say you are doing frame-wise classification. Let's say you misclassify a cat at index n from a video at frame n. It does not change the image at index n plus 1, the input of your system. Input of your system is independent from your prediction of previous frame, right? You always get the n plus mth frame as an input of your image classifier. Regardless of your output from index n, you always have the same image input from the video, right? So data distribution is static, that means data distribution is static. But what about robots and control, non-IID? If you take wrong action at AT, it directly changes the next state s plus 1, and this state, next state, becomes input of our policy function, right? That's policy function, pi. State, action. Let's see, ST, AT. But AT, ST and AT makes ST plus 1. That becomes another input of our policy function, right? So your input of policy function changes. That is the problem. Evaluate IID. You did something, in previous time step you did something, and then it changes input of our system, next input of our system. They violate IID. Why this is serious? Is it really serious problem? This is serious problem. And this is some seminal work in this field. The network must not solely be shown example of accurate driving, but also how to return from the road center once the mistake has been made. Let's see this example. This is your car, and in some reason, like a sensor error or some generalization errors or anything, there can be always errors, right, in estimation. Your car made us errors, and here your car is at this position. But in training data, you always have good trajectory, successful trajectory. So your training in training stage, your car is always on this demonstration, But with some reason, sensor noise or anything, your car suddenly have some errors, and now your car is at here. This is no training data. There is no training data on this position. Then how can your car successfully drive to the goal position? We cannot guarantee nothing. We can guarantee nothing. It becomes serious then for next state. There is no training data. So error accumulates. Once there is a small error, the error accumulates and we cannot do anything. That is the problem of behavior cloning, which is different from supervised learning. Supervised learning, all data points are IID, so that although your system made some mistake or errors at the previous time step, it doesn't matter because the input of your system is fixed, static. But your system in this kind of sequential control with reinforcement learning, let's say you have policy function, and input of your policy function becomes very different once you make a mistake in previous time step. Then bad thing happen. You cannot say anything about your model's behavior then, because this distribution becomes obviously too far from training distribution, so that we cannot guarantee anything. So let's see this in details. The standard supervised learning, like image classification. Strict IID assumption. Data points are independent, identically distributed. Error isolation. If the model misclassifies a cat as a dog at frame t, this mistake does not alter the image at frame t plus 1, right? Image of frame t plus 1 is from a fixed video. This system inherently recover because error do not propagate. The sequential control, robotics, non-IID paradigm, action state feedback loop, the agent current action AT, correctly determine its next input state as plus 1. Because, we have a transition model in simulator. And compounding failure, a single suboptimal action drifts the robot into unfamiliar state, and this degraded state is feedback into network as the next input here, fed back into next input, leading to cascade of worsening mistake. So it looks like very similar to supervised learning, but this kind of sequential control makes very different. In machine learning perspective, optimization is almost the same, but how agent interact with the environment is very different from supervised learning, because we are in sequential control. So why behavior cloning is exceptionally fragile, vulnerable to physical noise, minor real-world perturbations such as mechanical backlash or physical sensor errors, force the robot slightly off the expert clean trajectory. And zero-shot OD panel. Once off track, the robot encounters OD, out of distribution states, never seen in the expert data set, lacking the recover labels. The BC agent executes arbitrary actions, resulting in quadratic error growth and catastrophic system collapse. We will see this later, quadratic error growth. So although it looks like similar to supervised learning, this sequential control thing makes much more difficult than supervised learning. And so what is covariance shift? This is one of the representative limit problem of behavior cloning. Covariance shift is a mismatch between training and testing distributions. Training, as I said, police is trained on expert visited state. We have teleoperation, and then expert always do good job, right? Always do good job. But execution, policy visit at its own state. But as I said, because of something like sensor errors or anything, the kind of state distribution could be very different, because our optimized police function and expert police function different. The state encountered during task drifts away from the scene during training. Mathematically, we can also check how errors are different between supervised learning and the behavior cloning. So let's see the standard supervised learning. Error actually linear growth here. In standard classification of regression tasks, like classifying sequence of independent images, the data points are strictly independent and identical distribution, as I said, IID. No feedback loop. There is no feedback loop. That is important. There is no feedback loop. The model's prediction at time t does not influence the input data. Here, input data, it receives at time t plus 1. It is obvious, right? The error isolation, if the model makes a mistake with probability of epsilon at step t, that mistake is completely isolated. The input step at t plus 1 is still drawn cleanly from the true testing distribution. The total expected reward error is since the error do not accumulate or affect future state, we can simply sum the independent probability of making mistake at step t across the entire horizon, so that we have this one, right? Epsilon is a mistake probability, epsilon. And there are t frames. And obviously total error, the upper bound could be t epsilon, right? So the important thing is that the error is linear. So behavior cloning, things are different. Let's analyze worst case upper bound. Once the agent forced into out of distribution state, it has never seen any expert label for it. Therefore, we must assume a worst case scenario. The agent will fail with the probability of 1 for all remaining steps in that episode. And if the agent makes the first mistake at step t, which happens with probability bounded by epsilon, it will continue to fail for the remaining t minus t steps. Large t minus small t steps. To find the total expected error, we integrate this compounding failure over the entire time horizon from t equals to 1 to t. Total error, behavior cloning, mathematically, this is the probability of error and number of remaining failed steps, where t could be at the first frame to last frame, right? This is arbitrary t, but arbitrary t could be from first frame to last frame. And remaining things are just high school math. We can just do this kind of arithmetic progression, and then we can figure out that the error, upper bound of error, worst case, big O notation, t squared, right? Here, t squared, but the supervised learning, t. So mathematically, we can also confirm that behavior cloning suffer from large errors and more fragile than supervised learning. And then we will study more advanced imitation learning algorithm next time, such as Dagger. But as I said, interestingly, recent state-of-the-art VLAs simply use BC, as it does not time-consuming. It does not require. It does not require time-consuming rollouts. So we learned that BC suffer from some issues, like for example, covariance shift, or lack of action, missing action problem. But so let's say we have infinite money, infinite time, and then we can collect lots of teleportation data. Then with the help of large-scale data set, we can somehow address missing action problem and then the covariance shift. Because we have lots of data. So, but still, this kind of recent VLAs, at least in research community, the performance of this kind of VLAs are still limited with the simple grasping, picking up some object and then releasing it, or some grab gripper, only 2 fingers. There's no more complicated dexterous. Dexterous means our final project, interacting with object with the lots of finger articulations. Such kind of stuff is still haven't shown at all. But so they, I'm not sure you saw the video from Figure. The robot is doing some automatic job to process many packages for 100 hours. It is very interesting. So we are living in this era, and I think this very, I guess, and then the system is trained with the VLAs, with behavior cloning, because most of these days VLAs are trained with BC, with teleportation data. But, so there are many actually not solved problems still, like a dexterous manipulation or generalization to some unseen environment. Actually, that is the people. Each researcher has a different research topic, but in my opinion, dexterous manipulation and generalization to unseen, in particular outdoor environment, could be interesting and still not solved at all, I think. But anyway, these days, recent state-of-the-art VLA still use BC. It does not require time-consuming rollouts. So for example, like a PPO, we need to do rollout. We need to, because we need to get reward, right? If we need to get reward, then we need to do rollout, because reward is from rollout, right? Our policy function outputs some action, and then we apply that action in simulator or any environment, and then we get updated state, and then we get reward from updated state. That is the rollout to get, so that, but behavior cloning, as I said, it does not require reward at all, so that it does not require time-consuming rollouts. Rollout is very time-consuming. If you start a final project, you can figure out that rollout is very time-consuming in your physics environment. Doing something in physics environment, very time-consuming. But supervised learning or BC, it skips rollout, so it makes much faster. That is actually necessary to utilize large-scale data. Large-scale data, if we do rollouts in large-scale data, the training becomes too slow, so that we can, maybe we need to skip rollouts to utilize large-scale data sets. That is the reason I think why these VLAs just use BC without sophisticated reward design or rollout design to utilize large-scale data sets. And this is the sentence from OpenVLA. OpenVLA is from 2024. Of course, these days more advanced VLAs are introduced, but OpenVLA is one of the seminal work. As you can see, once actions are processed into sequence of tokens, OpenVLA is trained with a standard next token prediction objective here. Cross entropy loss here on the predict action tokens only. Cross entropy means there's no PPO, and just use the behavior cloning. So it doesn't mean what we've learned is meaningless. It does not mean what we've learned is meaningless. What we've learned is still important, and there are still many issues in these days VLAs. We need to address them, and then the knowledge and reinforcement learning, exploration, such kind of stuff is still very important. How can we combine them? How can we combine exploration-based RL? But how can we address the time-consuming rollout problem in time-consuming RL? And then how can we utilize large-scale data like BC, likewise BC? That is, how can we combine them together? That is a some these days research topic, I think. Okay, and any question? Next time we will study Dagger, I think, the more advanced BC algorithm.